Analyzing implicit functions. Similar to curve sketching with explicit functions, the same type of analysis can occur with implicitly defined functions or relations. With these types of curves, implicit differentiation will need to be used with one or two extra steps. The first one being solving algebraically for dy over dx, and the second one being substitution. Let's look at a few examples to better understand these concepts. Here's our first example. Consider the curve x squared plus y squared is equal to 100 in the xy plane, and answer the following questions. Determine whether the curve is increasing, decreasing, or neither at the point -8, 6. Then determine the concavity of the curve at the point 6, -8. Let's get started. We're going to begin by implicitly differentiating our curve. So the derivative of 2x with respect to x is going to be 2x, plus, when differentiating y squared, we're going to have 2y times dy over dx. And then on the other side of the equal sign, we're going to have 0, because the derivative of any constant is 0. Next, we are going to solve this equation for dy over dx. So we can subtract 2x to both sides and have that 2y times dy over dx is equal to -2x. And then we can divide both sides by 2y. To get that, dy over dx is equal to -x over y. The step in between would show that we would have dy over dx is equal to -2x divided by 2y. And since we have coefficients of 2, they cancel each other out, leaving us with the -x over y. And now that we have solved for dy over dx, or our derivative, we can determine whether the curve is increasing, decreasing, or neither at this point, -8, 6, using substitution. We're going to substitute -8 in for x and 6 for y. And when doing so, we will get the negative of -8, which is positive, divided by 6, and 8 over 6 reduces to 4/3. And then since the derivative, when evaluated at the point -8, 6 is positive, our curve is increasing at that point. Now let's address the second bullet point in this question. Determine the concavity of the curve at the point 6, -8. Well, we already know that our first derivative, dy over dx, is equal to -x divided by y. So what we're going to do is we are going to find the second derivative and simplify. And since this first derivative ends up having a quotient with two different variables in it, we are going to need to use the quotient rule here. So we're going to have the bottom, y, times the derivative of our top with respect to x, which will be -1, minus the top, which is going to be -x, times the derivative of the bottom with respect to x, which will be dy over dx, all over the bottom squared, which will be y squared. And now in order to simplify, we have minus a -x, so that becomes plus a positive. So we can move this positive x times dy over dx into the beginning and then have minus y at the end. So we will have that our second derivative is equal to x times dy over dx minus y, all divided by y squared. Notice that we have a dy over dx here in our quotient. And we already know that dy over dx is equal to -x divided by y. So we are going to actually substitute -x divided by y in for dy over dx in our quotient. And when we do that, we are going to have that it is equal to x times -x over y minus y all over y to the second. And now what we're going to have to do is in our numerator, we are going to have a common denominator, because this first fraction, when we multiply it together, it's going to be -x squared divided by y. Well, this second term in our numerator is y divided by 1. So in order to add or subtract it to what we have in our first fraction when simplified, we need to have a common denominator. So we're going to multiply the top and bottom here by y. And y divided by y is 1, so it doesn't actually change the value. And that will end up simplifying to negative x squared over y minus y squared over y, all divided by y to the second power. And then we can rewrite our terms in the numerator as one entire fraction, negative x squared minus y squared, all divided by y. And then we can rationalize by multiplying both our numerator and denominator by 1 over y squared to get negative x squared minus y squared divided by y to the third. Notice that both of our terms here in this numerator are negative, so we can factor out a negative 1 there to have negative x squared plus y squared all divided by y to the third power. Now notice x squared plus y squared is equal to 100, so we can actually take 100 and substitute it in to our numerator here and then simplify. So we will have negative 100 divided by y cubed as our final answer. And now that we have our second derivative solved for to be negative 100 divided by y to the third, we can determine the concavity of our curve at this point, 6, negative 8, by substituting our y value of negative 8 in for y cubed. And when we do so, we will get that it is equal to negative 100 divided by negative 8 cubed. And when it simplifies, it'll be negative 100 divided by negative 512, which will end up being positive 25 divided by 128. And then since our second derivative is positive, at this point, 6, negative 8, the curve is concave up. Now let's try another example. Consider the differential equation dy over dx is equal to x times the sine of y, where y is equal to f of x. Determine the relative extrema that occurs at the point 0, negative pi over 2. Let's get started. We can determine the specific type of relative extrema that occurs at this point using the second derivative test. If we find the second derivative and then evaluate it at this x and y value, we can determine the concavity at that point and therefore whether it's a relative maximum or minimum. So let's get started. We need to begin by taking the second derivative of this differential using the product rule because we have two separate terms here. We have an x and we have a sine of y. So we have two things that we are going to be differentiating. So for our product rule, we will get the first, which is x times the derivative of sine y, which is cosine y, times dy over dx, plus our second, sine of y, times the derivative of our first, which is just 1. Notice that we have a dy over dx still in our second derivative, so we have to use substitution and take x times the sine of y and substitute it in for dy over dx. And now we can simplify it. We have an x times an x, so we'll have an x squared, and then we'll have both cosine of y and sine of y with our first term, and we'll still have plus sine of y as our second term. Now that we have our second derivative solved for, we can evaluate it using the coordinates from our given point to determine the function's behavior and the relative extrema that exists at this point. So we're going to have 0 squared times the cosine of negative pi over 2 times the sine of negative pi over 2 plus the sine of negative pi over 2. We have 0 for our first term, so this whole first term cancels out, and what we have remaining is the sine of negative pi over 2. Well, the sine of negative pi over 2 is negative 1. Since the second derivative is negative, that means our curve at this point is concave down, making 0, negative pi over 2, a relative maximum.